When we set out to plan the Illumes for this year, I wanted to do an episode on tool design focusing on attributes. The first thing that came to mind was the often used name attribute, a simple string attribute used to name the pieces and assemblies in our SOPs, setups, and asset tools. It's surprising to see how often a name is used in so many of these setups that we use every day. From rigid bodies through to packed primitives in and out of instancing, Alembic and USD, there's always going to be a name attribute. In this Illume, we will just cover a few of these areas. Rigid bodies, where a name played its first important role. That in naming packed primitives, alembics, and USD primitives along with import and export tasks. KineFX, use name for joints. And then there's volumes and VDBs, where volume names are critical to working with them in Vex. Also, many labs tools make use of the name attribute as well. And many third-party tools such as MOPs, which we're going to have a look at later in the day. And following this, we're going to have an interview with Moritz Schwind of Entagma and Henry Foster, the chief architect of MOPs. It's surprising how often the name attribute is used, and as Houdini architects, we need to understand many of the uses of the name attribute. When you wire 3 or more SOPs together, you're not only building geometry procedurally, you're a designer, a tool designer. A Houdini architect relies on a foundation of attributes. There are going to be attributes, default attributes, normal attributes, and as Houdini architects, it's interesting to study the design choices that other tool designers make as well. The recipe always involves SOPs, which in turn create and use attributes bound on geometry. Whether it's P, N, CD, alpha, P-scale, and so many more optional bound attributes. In this Illume, we will be in the Houdini the entire time as we peel back the setups we commonly build to see how these specifically named attributes are used. It's all in a name, the names we choose as architects to use in our tools and setups. The Illume today is for most users in Houdini and familiar with basic tool skills to seasoned veterans who want to add Houdini skills as well. I'll go out on a limb and say that understanding attributes is the fastest way to understand how a setup works in SOPs and in Houdini in general. If you don't think so, then why are you constantly middle mousing on SOPs to see what's going on? The better you are at reading attributes, the less likely you are to get lost. It's time to read the attributes by their name and trigger ideas for future use. It's truly all in a name, so let's get started. So it's all in a name. The first area that we're going to take a look at is how the name attribute relates to rigid bodies. And that's the first place inside of Houdini where we started to use the name attribute in earnest. It was an attribute we chose to simplify how we worked with massive numbers of rigid body objects inside of the bullet solver. Prior to name and prior to the bullet, we actually had to create individual objects. So let's start off with the table. I ripped off from the side effects content library bar scene, and I applied some materials to it in a simple material network, tabletop, stand, and base. And if you want also, you can actually substitute in the squab geometry. It too has an internal material as well, but let's work with the table. And the first thing we want to do is inspect this, so control middle, and that brings us up the detail attributes, and we can see there's a shop material path on there that's button for the material. We also notice that there's some groups on there: table base, table stand, and tabletop. So if we want to use name in place of group, because groups can be very inefficient once we start dealing with numbers of geometry, we can put down the name SOP or the name from groups. So the name from groups allows us to take any groups and build a name attribute out of it. We can see that it's really geared towards rigid bodies. It's commonplace in rigid bodies to use this group mask called piece to drive into name, piece 1, piece 2. And we'll see that as we start building up this rigid body simulation. So if you want to generalize this, we can basically just say, well, we want all of our groups to now become name attributes. And I'm using the technical desktop right up from here in case you're following along and you want to work this way. It opens up with the spreadsheet itself already open. And if you go to the primitive group list, we can see obviously that we have our name attributes, and they're based on the groups. At this point in time, we could blow away the groups if we wanted to and keep on working with just using the name. We'll also notice here shop material path. And shot material path is also very powerful in that it also gives us the same delineation between the various different pieces. So if we take the name based on tabletop, we can see tabletop has got an associated material because we assigned the materials based on groups. So we have a nice consistency here. We'll see later on how shot material path actually saves us because the rigid body workflow will pretty much override this name attribute with all kinds of cluster attributes and that moving forward. But that just shows you how name is critical in how things are being progressed further forward. So let's build a simulation network. It's pretty easy these days. We have this tool called RBD configure. Just use basically RBD configure. We can configure some RBD pieces. We can put that down. And we can see here that we now have done some pretty interesting things to the data. We've actually packed the geometry, and you can notice that we've lost the material definitions because that's a limitation of our viewport. If we wanted to do a quick render, let's actually just select the render box and we open this up. We still may not get the materials because we might have to affect the shader itself to pick up these material properties. And to prove that, we can actually unpack this later on. We just put down a simple unpack and we can bring back our geometry and our materials are magically back there. As I said before, if you wanted to render packed materials on the material itself, there's an option on here that allows us to use packed colors. So if we select all three of these materials, we can turn that on. And now if we go back to the RBD configure, let's see if our render will actually pick that up now. And it doesn't. So, so the way forward right now is to do unpack. We could apply materials later on. Again, it's a limitation of the GL viewport. So RBD configure, and we're going to go back here. And we'll notice that rigid body configure actually moved that name attribute to points. The reason being is because in RBD, we factor everything into points using these packed fragments. And packed fragments are an efficient way for us to work with primitives on the GPU. We just lift one single primitive on the GPU that contains packed fragments. And then we use point transforms on the GPU to move these objects very, very efficiently, which gives us the ability to scale up with Bullet. So these packed fragments are very important workflow inside of rigid bodies, inside of Bullet. And of course, the next thing we can do is we can now put on an RBD, an RBD simulation, so an RBD Bullet solver, wire that down. And because we actually have some constraints in here as well, we can wire these as well. So the constraints in proxy geometry, we don't have proxy geometry defined here, but we might as well wire it up just in case we want to work forward. And now we have our tabletop. One of the things we can do with our tabletop, we've now got to position it. And let's move this up here. And we have a nice tool called match size. Match size actually allows us to center our objects on the primitives. It's not the best name, but we can actually justify y by min, and then we can place our table. But again, a table sitting on the ground is going to be very boring, so let's put a transform on here. And the transform, we can move the table up. So let's just move it up a few units. And now let's go to the RBD Bullet solver. Let's add some ground. So ground plane in the ground tab, and then we can press forward. And we can see our table falls over. Now one of the things we can do is do an RBD material fracture. After the RBD configure or in place of the RBD configure, we can put down an RBD material fracture. So with the material fracture in place, let's replace the RBD configure with the RBD material fracture, and let's see what happens to name here. We now see that name, still on primitives, has now got suffix on it that denotes that it has, for instance, table base now has 0, 0, 0, 1. So all the fractures with this specific tool get placed in the appropriate chunks now, but there's a prefix of table base for now. And that's important, because that is how the bullet solver actually solves these pieces. And so the material fracture, we now want to take a close look at this and see how the actual fracturing is happening. With the tabletop is not fracturing. So we know that by moving the noise offset and changing the frequency, we can change how that shattering happens. And I'm just going to move the noise up through the table until I get something that I kind of like. And let's move it down a bit. That's pretty good. And we can increase or decrease the resolution and the cutoff density as well as to how we want to fracture these things. But now let's wire. I'm going to cut all the wires here, and now I'm just going to wire just the rigid body material fracture into our workflow and press forward. Now there's a common technique in bullet that if you have pieces that have the same name or ID, they will basically get the same transform. And we have a tool that does that. And that particular tool is called RBD cluster. So if we put on RBD cluster, it will actually consolidate the names of the pieces. And we can take a look at the help as that pops up and read more about how clustering works. But in essence, what it does is it uses the name attribute, and it basically consolidates by name. And adjusts the name primitive attribute to combine pieces into clusters. In other words, we're just making pieces with the same name. So it's a very convenient way of building efficient groupings of pieces to make things look more realistic as they fracture. And so RBD cluster, and there's a few different ways that we can visualize this. We can turn off the materials in the viewport first of all, and you can see that we're already visualizing these attributes. But if I hit the control middle mouse button on here, you can press name, visualize the name, or the cluster pieces as well. Another way to do that is to just go into select mode with your current selected node, and up in the very top we have select name attribute. So name is so ubiquitous inside of Houdini and the various many tools that there's actually a nice placeholder in the select. And here we can see all the different named pieces in our various different groups. And as well, we can select them in here. And we can see here that the whole tabletop got clustered together. And so we can loosen that up a bit here with the detach ratio. And you can see here that we can detach more and more pieces from the various, when we coalesce the different name into these cluster groups up above. And we can actually change the seed as well. So lots of control over that. Now if we press forward, we can see that our table is now going to smash. And of course, those consolidated pieces by name are now going to be all nicely consolidated for us. And so to escape this, you just simply hit escape. And we're now back into visualizing as well. And again, if you control middle on that, you can remove that visualization as well. Now, the unpack, how does that work again? So if we take a look at the unpack, what happens here is the name comes back, but it's being completely changed. And the name is on the cluster on the primitive attributes itself. Now, the simplified version of this, of doing RBD fractures, there's an awful lot happening behind the scenes. I can tell you that the bullet solver itself needs to have this name attribute on the points themselves. And all of this got consolidated and made very easy for us. But now we're going to put on our tool design hat and see how we can work with name attribute at a much lower level. And then we're going to peer into this RBD bullet solver to see how that name actually was used. And the more we understand how this name attribute is used, the more we can actually get in here and actually affect the design of these tools. So the first thing we're going to do is do an old school voronoi fracture. So we're going to put down a voronoi fracture node. And it takes two inputs, the geometry to fracture and the voronoi cells. So let's actually put the geometry to fracture and let's create some points. And a common way is to use an ISO offset. ISO offset allows us to build the same geometry but in different representations, you know, fog volume, SDF volume, tetramesh. So we're going to use a fog volume. And I always set this to 100 to get a nice resolution volume. And then we can scatter points into volumes. By default, if you pass a volume into the scatter node, it will actually scatter points, right? And those become our cluster seeds for the voronoi fracture. So now we can wire that in, and we can see that our geometry is now fractured into a whole bunch of different pieces. And again, let's see what happened to names. So we can see that names now completely overridden. We can see the name attribute here is set to tabletop, but over here the name attribute is now completely obliterated by using piece. That's fine. And if we middle mouse on this as well, we'll see that we're still dealing with polygons. So we don't have to pack at this point in time. And so we can actually just put our DOPNet down, or pardon me, we can put down a DOPNet. And let's start working and building up a bullet simulation from scratch. DOPS can be a little bit obtuse at some point in times. It is its own type of a network, but let's see if we can all follow along. So we're going to start off with a bullet solver, or we actually have a generic RBD solver. Go with the bullet solver. And when we placed on the bullet solver, we can now wire that up to the output, but it needs input geometry to work on. So if we hover over this node, it can say objects to be processed. And if you also middle mouse on this or right mouse on that to you know, to put down a tool, we can add some more tools. But what we want to do is put down first of all a ground plane, and we can wire that in, and that just builds us an infinite ground plane. And let's put down a merge. So we're actually assembling the objects that we wish to simulate. And RBD packed object is the key tool that we want to use. And what this does is it loads in geometry and then packs it up for us. And in this case, in the RBD packed, what we want to do is point it at our input geometry. And we can actually choose here first context geometry. And what this means is, if you're unfamiliar with it, the first input. So this context option 1, 2, 3, and 4. So we can actually pick up our geometry from there. And we can see that our table's in the middle, so let's go up here and let's steal this transform over here. I'm just going to alt-click and put a transform down below here. So we can steal that, and now we can see that our table is a bit off the ground. Actually, let's make sure that this match size is also being picked up in here. So I'm just going to use the Alt key to pick up these wires. I'm just holding down Alt and dragging, and then I'm just basically going to take match size and I'm going to drop it in between here. And now we got our match size. And that allows me to move this dot over here so it looks a little bit nicer. And now we got our table up. And back into the DOP network, RBD packed object merge. We need to add some forces. So there's a gravity force. We have all kinds of different forces in DOP. You just tab force and you can see them. But now we're applying gravity, and now we press forward. And we don't get anything. The reason why is it does require packed geometry. So let's go back up. And in here, what we need to do now is add an assemble operator. And we can do that before the transform. And assemble is specifically designed to create packed fragment geometry for rigid body simulations. And this particular node, again, will work with piece attributes, and it will work with the name attribute if it's present, which it is doing right now. But now we've got, we're going to have packed fragments on here if we do create packed geometry. Now we should be able to play our sim forward, and we get our table dropping. And we could also use the configure pieces if we wanted to RBD cluster in here as well. It'll take these names and work nicely. But now we can see clearly what's happening. So on the RBD pieces, we can see here that now, because the DOPNet I said requires the packs to be on points, That's exactly what the assemble operator does. It does assemble geometry ready for the DOP network. And if you dive inside of the RBD material and clusters, you'll see that there's an assemble in there that gets used to do this work. And if we dive inside of the DOP network, we'll notice that our data tree changes. And in DOPs, we actually represent these simulation objects. And there's two right now. There's the ground plane and the RBD packed object 1. If we open this up and take a look at our geometry, this is the actual geometry that we're simulating. And it requires the name attribute to be on points. You can see there's also a tremendous amount of other attributes that are added to the points as DOPS solves every substep. It will write the geometry into this holder so that it's available for the next simulation step. And here we have our name pieces. And again, that is what's driving the identification of different pieces inside of the Bullet solver. And that was the redesign of Bullet way back to get us to the point where we can simulate hundreds of thousands of pieces now by using point manipulation of this name attribute. And then the DOP network. So what do you do after this? We can unpack, as we saw before. Let me go back up here again. We can unpack. And we can get back to our regular geometry. But we'll notice that the name attribute is still present, and we got all of these attributes that we need to work on. But we are also going to take a look here at the name. We can actually isolate just the name. And so let's turn off hide all attributes, and then we can just take a look at the name attribute, because there's a couple interesting things that have happened. We'll notice that there is no name attribute right now, but we can transfer attributes. We can say star, and now we get our pieces showing up. But there's some problems here. We'll notice that there's a whole bunch of empty pieces, and you wonder what that is. So let me control click on this and control middle on this, and let's actually turn that, because we are still looking at the path attribute, which is all those numbers that were showing up in the viewport, because we had that visualizer still on via the control click on the info. So now we got to unpack. And so what are these blank pieces? Well, we can, using the name attribute, we can put down a blast. And there's a couple different ways we can do this. We can do this manually, or we can use the viewport. So let's use the viewport. We can go selections in here. And as soon as you select, it actually changes your viewport selection to work on names. So if we say there's empty string, and then we hit enter, it's our ground plane. So that now we know that the DOP object will actually bring in all the simulation objects, and we can very quickly isolate back to just our basic table. And then we can play forward, and we can see moving forward. So again, all in a name, right? So all of this workflow is really set up nicely to work with the name attribute. But we can see how the name attribute changes as it flows through this specific network. So it can be very confusing as a novice user or an intermediate user. You're going there, what's up with name? So we've seen name used within a suite of tools inside of Houdini for doing rigid bodies. Name is used for doing a whole bunch of other things as well, and a lot of tool designers will lean on the name attribute to efficiently process geometry and work with pieces of geometry, as opposed to using groups, which I've mentioned before is very slow. So I'm going to open up an example file and show you a bit of that. So it's Labs building generator is what we're going to look at next. So the building generator, it's a tool that requires you, it's a typical Houdini tool that requires you to build a lot of the pieces in a very specific way. But once they're built in that specific way, can fit within a really powerful tool set. In this case, I've just taken a really basic grid at the 0 to 1 using match size. Placing it at 0 to 1, you can see, and let me turn off my fog background. I got fog on. And let's turn that off and save as default, so that it doesn't come back haunt me. And we can see here that it going from 0 to 1 and 0 to 1. And you can make it any size as long as it starts at 0 and its bottom is placed at the base. And we can take a look at the help. You can read all the help on the building generator to see how it's actually done. But another important piece that you need to do is to give that piece a name. So in this case, we've called this generic chunk wall. And now I've just got a switch in here. We're going to take a look at the building generator in a minute. But now we can put down the building generator. And let's start from scratch. I'm going to blow that away and put down a building generator. And it takes several inputs. First of all is blockout geometry. So I've just created a box, and this box is going to be the volume of my building. And this volume, it will literally fill wherever this volume is located. So again, I use a match size to ensure that it's placed on the ground and 0, 0 and centered across everything else. And then we can wire that into the building generator. And we can see that the building generator already has some basic setups inside of it. It can actually construct buildings without having any secondary inputs from the volume. And we can change the floor height. And you can see you get nice previews. And these placeholders in here are where the different pieces of the panels will go. So we can see that this tool really likes to, you can define pieces to fill the wall panels, the spandrels. You can do the spandrels that cover up the floor and the ceiling spaces, as well as the base and of course the roof, and also corners. One thing that always gets you in building generation is the corners and the exceptions they create. The building generator can build all of that for us. And not only that, it actually puts everything into really nice named groups for us. So again, we can control middle on this, and we can press on the name. And we can see all the various different names. And if we actually want to see the names, again, just hit the select button in the viewport, select by name attribute, and you can see here, you can pick and see all the various different pieces. No patterns are available here. So hitting escape to get out of that. And now let's see what happens when we do put some panels in there. And that's the second input. So we can see the second input is the building modules. And the building modules, as we can expect, are going to be all of these different pieces that we can supply by name, because that's how they're referenced inside of here. So if we open up here primary and secondary wall face module pattern, we can choose wall, which is the name of the wall pieces that we've applied at the top. And now we can see that we're actually using our wall element from the grid, and it's given a specific type of a color. So that's the basics of what we're doing. We can also supply concave corner modules and convex corner modules. Obviously concave is when you have a corner that's facing outwards, and concave is if you had the building actually had an interior to it. You'd actually get some concave pieces, and it would require different corner pieces, whether it's convex or concave. You can define all of that. And you can also customize various different floor overrides to create different increments in height. Let's say you want to go up 10 stories and then have the 11th story be a bit smaller, the first story a bit higher than the other ones. You can actually do floor overrides as well. But we're more interested in working with these various different pieces. We can actually identify floor colors as well. We can build attributes. But the name attribute is critical in building these systems. So if we go to the building generator, and if we actually go to labs tools on the website, you can actually download and take a look at the various different, there's a really nice example file which we're going to look at next. So now let's actually take a look at the website where the building generator is in from labs tools. And here we can see that in labs under tutorials, building generator, we have a really nice quick start that shows you how to set everything up. It shows you how to build your modules, as I said, on the YZ plane, front, lower right corner. So there are some restrictions to make these modules play nicely within this tool. And as I said, it's easy to get that to go with the match size SOP. And then we can block out the area where we wish to build the building. You can do some very complex or very simple blockouts. You can use the Boolean operator with boxes to do that. And it's designed to work with BSP brushes inside of Unreal as well. And Unity also has blockout tools. So this is designed to build very nicely, also not only in Houdini, but also be able to take this volume geometry from Unreal and Unity. And it works very well in that capacity. There's some videos online if you wish to see it. But we're more interested in, as architects, seeing what motivates this. And I said the big part of this is using name to define the modules, and taking a look at this. So just download example. If you download this example file, that's what we're going to do next. So if you want to do that, pause, download the example, and fire it up in Houdini, and that's what I'm going to do as well. So this is the downloaded and opened up building module file from the tutorial site. And we can see that it's quite a complex example. And again, as I said, all the panels are defined by name. And taking a look here, we have the three different components. Here we have the blockouts going into the SOP building generator, so we can take a look at what that looks like. And it's just a couple Boolean boxes. Again, BSP brush is feeding into this, and Unreal would work just as well. The second input is all of our different modules. And here we can see here that we've loaded in all the modules in a stash operator, which just is a lightweight internal cache of all the different pieces. And we can see that these pieces already have names assigned to them. So when they were created with the building generator in mind. And they're all starting from zeros, from the origin, moving outwards. So 0 out, facing in the right direction as was outlined in the documentation. Now, as you can see, all these panels are basically placed on top of each other in a very game-friendly format. You can save these as prefabs, get loaded them really quickly, and it works very well in a game engine's instancing platform. It's also a great way to design just a general building tool, because when these modules are placed at the correct position, you can move forward. Yes, this can be proceduralized as well. I've written many procedural systems that will take these panels and normalize them to 0 to 1. The problem you have is architectural features really like to be built in world space, in world sizes. So the modules should remain at their real scale relative to the other pieces, as well as being in the right orientation. But again, name. So we actually have a whole bunch of different names. Now, there's a couple tools that really help us out here that are added to the building tool. So we have this tool called SOP Align and Distribute, which is a labs tool, labs align and distribute, which was designed to lay out all of these different pieces. And we'll notice a weakness in this tool. That's according to me. I'm saying if I was going to add an RFE to this particular tool, it would be to put the name or the name attribute underneath these pieces, because one of the things this tool does is it gets rid of name. So how can you associate the name of each panel? You can use the path. So there is a path available to us as well, but it's not the name that's used by the system. So it requires you to have a certain level of discipline in this. It would be nice if there was a name attribute underneath the panel, so you know what you were looking at, and you could pop this up on a secondary window, for instance. You can put a preview window up, and then you could use this to reference the names as you fill out the building generator pieces. But I digress. I mean, this is a nice feature that we could add in the future. But regardless of that, we can now go into the various different pieces. And here, there's a bit of logic here that was used to color the windows. So isolate the various pieces in the building using a split operator. So we want to split all the pieces with window, and we wanted to tag those windows with glazing, and so with different materiality. So you can definitely do that as well. So that's what this bit of the network is, just to isolate those windows and give them a unique color. And then merge it all back together again. So we finally get all of our pieces together. And how does that play in the building generator? Displaying this, we can see that all the different pieces now are filled out. So by name, the facade module pattern is F2 window 1. Again, that's the name. And it's all using names, the name attribute, to define the different pieces as they go. So a custom tool used to build pieces using the name attribute as a way of creating pieces or panels to work with very, very efficiently. And again, an old school user might think, oh, you can use groups to do that, but name is far more efficient, and it is really a first-class attribute inside of Houdini. So use it as you should to build your tools. Now, one of the things with attribute wrangle is we can do some pretty interesting things here. For instance, sometimes you want your path to be the name or the name to be the path. And we saw this before, where you can actually create path equals path plus name, because one thing we're noticing here is when you're exporting a lot of these things, let's say to Alembic, the Alembic ROP just, what's my path attribute? And it's path. And sometimes we actually want to have the name of the module in there as well, because we don't know if the Alembic ROP is going to actually append name to that. So we can do an attribute wrangle here, and this string is string at path, so that means we're overriding the path, is s path plus s name. And we're putting a slash, so you can actually do string concatenation inside of this as well. And I think if I can make this larger for the screen, yeah, but yeah, so that's s path equals s path plus double quotes and double quotes slash plus s name with a semicolon to terminate that, to build our path to actually have the pieces on the back as well. So when we export this via Alembic or USB, it'll come in nicely, and that's exactly what I did here. So there's a ROP export. We export it to building.abc and save that to disk, and then we can load that back in, and we can actually see our path loaded in nicely. And that will work very well when you're migrating this asset to other applications that have a different way of managing organizations, you know, using a scene graph or some sort of tree to modify the geometry. Now they use the export as well. Once again, output processing, it will actually use either name or path to export our geometry. And if we go into a local LOPNet, which I added with a SOP import, we can actually see here no roof. So we got to figure out why that is. But we can see here, if we add a under the new pane tab type, if we go to Solaris and add a scene graph tree, we can see here that path was used to create the hierarchy within the scene graph. And so that was important to actually add that name attribute to the path, so it picks up nicely inside of here, and we get all the different pieces inside of the building coming in very nicely inside of USD. And another thing we can do is we can clean up the scene as well. Here's a simple subnet that I added that just basically can clip some of the data out, delete some various attributes, merge in a ground plane and normal. I believe this came with the scene file. So, and then of course there's the point cloud. And what's nice about the point cloud is that this using these pieces saved to disk via FBX. You can actually load this into a game engine, and the point cloud contains all the attributes that link in to do the proper instancing inside of your game engine. And also to do instancing inside of Mantra as well, or any other render engine if you set up the instance workflow correctly. So it's a really powerful tool for building, for doing building construction. And heavily using name to do a lot of the heavy lifting of building the logic and assigning the panels and building the UI for this. So next up is KineFX. Let's start a new file. And let's put down just a generic piece of geometry, dive inside, and let's go back to our geometry spreadsheet here, reduce its size, and we're just going to add a simple L systems tree. And if you're fairly familiar with KineFX, that's great. If not, it doesn't matter. We can just follow along, and we're going to actually see, if you are fairly new to KineFX, to see how and why name is actually a critical piece to the design of a lot of the tools. If you're working with just arbitrary point geometry, there's a really cool operator in the KineFX tool set called, let's do this, it's called skeleton. And if you put this down, what it will do is it'll try and build a skeleton out of your input. But there's an even better operator in here called the rig doctor. And the rig doctor can take any geometry and then allow us to create a basic quick rig of all of our any incoming curve geometry. And it looks to see where there's fused points, and it'll build all the various different attributes to build an actual IK chain on top of our geometry. So these are all joint based now. So these are all joints in here. We can change the way that it looks inside of here. Now, what attributes are created? So right off the bat, we can see that there's a name attribute. So every bone, or every joint, I should say, has a name associated with it. It's basically the point. So every joint is given a name, and that is actually using the name attribute. And there's no primitive attributes on this right now. And one of the things we can do is we can use a skeleton operator, and we can start working on this hierarchy. And you'll go, Jeff, where's the hierarchy? I'm not seeing any hierarchy. There is one defined if you can parse through the intrinsic data on the primitives themselves. There's some intrinsics that are used in here to determine how things get working. But there's an easier way. So we added a widget on many of the rig tools called the rig tree. So if you right mouse on the skeleton, you choose rig tree, you'll actually get an outliner. And in here we can actually see our hierarchy. Now the skeleton SOP is a bit fussy in terms of being able to, you can right mouse on here and you can do all kinds of work on these various different pieces. But in previous versions of Houdini, if you're an old school Houdini user and you're going, wait a second, I'm changing an attribute on a SOP, that's going to lock it. And it's not going to be able to keep those changes. And you would be pretty much in the right thought pattern. So it wouldn't surprise us that there's something that we'd have to do above the skeleton to make this work. And that is called stashing. You'll notice that there's a lot of options in here to stash the input, stash merge input, and working with stashes, in other words, to capture the current state coming in. But I like to actually use what's called the rig stash pose. And if you put this above the skeleton, what this means now is that anything that's coming in, it'll stash this pose, and now it allows me to work on it in a way that I can be destructive yet predictable. So in other words, you pretty much have to be assured if anything's coming in here. If I am using the skeleton operator to do some hand massaging on this, definitely do that. Oh, name is fair game. Nothing stopping you from putting a wrangle in here and renaming all of these attributes procedurally. Nothing stopping you. But we're going to play within the rules of the KineFX tools with regards to skeleton. So now I can say there's point 12. I can right mouse point 12 and I can now rename this. And let's call this point 12 underbar Jeff. And now we can see that in the input name, if we take a look at the name attribute, let's actually hide all these attributes and just show the name attribute. There's point Jeff down there. So again, name is intrinsic to the way that the way KineFX works. Now, let's say, for instance, you wanted to add a prefix to all of these joints. You know, many times we're working on rigs, and you know, there's tools in here graphically to do this. But let's see what that exercise would look like inside of SOPs if we were to use old school tools. Remember, because KineFX, any SOP is fair game. A joint's a point. So we can do whatever we want with it. And the rig doctor can save us out of many different crazy situations we might get ourselves into. So let's try putting an attribute wrangle. And again, we're just going to use some string munging. We're just going to go inside of here. And we want to add a prefix to name. That's pretty easy to do. So we can do s at name. I always like declaring, I mean, a lot of shortcuts out there. Oh, you don't need to use S for named attribute, like for known attributes inside of Houdini. I like to be very explicit and leave the shortcuts for the fancy pants people. I'm very deliberate. So S at name equals, and we're going to put in here, we want to call this base rig. Let's put a prefix on here, base rig underbar. And we want to add, with just the plus operator, S at name. So we're taking the incoming name and we're just prefixing with base rig. And sure enough, we've now got base rig all over the place. And again, if we right mouse on here, we can now see, even though the outliner may or may not be available on the right mouse button on an operator, we can see here some operators have the ability to open up the tree and other ones don't. It will follow along with your current selection. So if you have this up and running as you're doing work, it'll actually show you the results of what it is you're doing. You won't be able to do anything with the tree when you're working on an operator that is not set up to work with it, but it's still available for you and you can still keep on working. And nothing is stopping you from doing more and more rig stash pose and then more skeleton operations as you work on your different rigs. So let's put on another skeleton. and so on and so forth. So you just keep on working, and you can do a lot of work, you know, mix and match old school Houdini workflows along with the newer you know, tools that are available to us in the KineFX. We can copy selected joints, paste joints on parent selections, orient selections. So there's a whole bunch of different operations that are applied. Again, all in a name, right? And now for something completely different. I'm going to start a new file, and we're going to take a look at how name relates to volumes, and how critical it is to understand and manipulating name as it pertains to working with volumes. So we're going to start off with the rubber toy. And because the rubber toy isn't manifold, we'll just put down a Boolean operator. Oh, and I might have, so let's double click inside of here. Now we're inside of geometry, and let's put down a Boolean operator. Let's do a Boolean union. All this is just a preset that sets up the Boolean SOP such that it makes it into a manifold piece of geometry, and we can see here what work it's done. So yeah, great. Now we're going to put down an ISO offset. ISO offset is how you create volumes for Houdini's own internal volumes, and at the same time we're going to put down a VDB from polygons. And shadow the two, because believe it or not, the same name worked the same way in wrangles and also in volume VOPs. It doesn't matter whether it's a volume primitive or an SDF primitive. It's the same. There's no differentiation between the two. So in this ISO offset, I always set it to 100 just to get a decent resolution volume. And in the VDB from polygons, I believe it's something like 0.02 gets us to the same resolution. And we can see that we're at 100. And we're at about a 107, so we got a pretty good approximation. This one is set up to volume data, and so looking at the ISO offset first, we got fog volume, ray intersect. Right there is name, and many times you leave it blank. And if we go to the primitive data, we can see that there's no name attribute. But if we fill in the name, let's call this density. It's common to call any volumetric data as density, and any surface data as surface. So ISO offset, you can see with the volume support inside of Houdini, it's very atomic. You're always adding a lot of operators to work your volumes. And so instead of a FOGS volume, we're going to do an SDF volume. These are old tools, old but trustworthy. And for density, we're going to use surface. So we usually call SDFs surface. And taking a look at the volume VDB, alternative, here we can see we have all the options available to us. We have a distance, which is surface, and then we have fog set to density. So yeah, Houdini volumes versus VDB volumes. Yeah, this is just for history. There's probably a good argument to have us sort of clean all of this stuff up and to make it a little bit easier, but hasn't happened. I think VDB grids are used a lot more frequently these days than our volume formats, although it's good to know both. And so there's VDB polygons, and now what we can do is, so we have our named sets. We can now merge these various different things together. So let's merge them together, and we can merge our two volumes. So we're working on equivalence, working with equivalent volumes. And now we can see here we got volume density and surface and density. Actually, we should call this surface, what I'm saying. So I'm sorry. Yeah, surface. And this is called surface density and surface. Yeah, I got it right. Okay, so we're merging those together. Now, so we can now do some work on this, and we can put a switch operator down here because we're now going to do some logic inside of a volume VOP. And it doesn't really matter what the volume VOP is going to do, but let's put down a volume VOP. And a volume VOP is very similar to volume wrangling and attribute wrangling. The only thing you cannot do in a volume VOP is you cannot initialize a new volume, a net new volume. For instance, if we wanted to write into a CD volume, we would have to create those volumes ahead of time. And so if we dive inside of the volume op, we can actually see very quickly what it is we have to offer. Now, when we're inside of here, we can actually bring in our surface field, or the field that we actually had called surface. And the way we do that is just simply put down a bind. And if we want to load in that volume at the current sample position, all we need to do is just put down here surface. So by putting down surface, we now actually have access to our second volume by position. So it's basically whatever voxel is currently being evaluated in the density volume will also index into the surface volume and get us the same attribute. So for instance, and we're outputting density here. The one problem is our SDF is getting in the way of our display. How do we turn that off? Because, we have a nice fog volume in there, but you wouldn't believe it because the SDF density is obliterating that. So we can use a simple tool called the primitive operator. And the primitive SOP, we can actually go down in here and we can actually, we can either put it up in here. That's where our density is, and that's where our surface field is. We can actually go in here and we go into volumes, and we can just adjust the visualization here. And of course, I didn't show you this earlier, but all the attributes, including name, will show up in groups as well. So even though we have name groups, we will show you all the attributes into a name group as well. So we can actually work on the surface field. If name equals surface, it's really handy. We can now make that, we can visualize that isosurface as a fog volume. And this will come in really handy later on. Or we can visualize it as a rainbow isosurface, which is what the default is, or we can make it invisible. And now when we merge it together, that particular volume has an invisibility flag to it. And yeah, you need to remember that when that's on. So now we're back into our volume VOP. Now we can actually see what work we're doing. And now we can do really interesting things. For instance, we can multiply these two together and see what we get. So remember, the surface field is actually a sine distance field. So it's calculated at the time that it's generated. And that's the expensive part about building a sine distance field, is when you're authoring the volume file from whatever input. Once it's authored, you can access it extraordinarily fast to get distance and density. The distance along array, you can really quickly and almost instantaneously calculate the accumulated distance. But in this particular case, we just want to take the density and do something interesting with that. So we can, for instance, multiply the two together. And if we do that, wherever the density is 0, the SDF will be 0. So we can actually do that. So pardon me, if I put that into the density. And then we can output that back into the density. And the problem we have, though, is the way that SDFs are calculated is inside is negative and outside is positive. So we could use a negate operator in here, and that will simply flip the sign. If we drop that down in here, and now you can see we're starting to get something really interesting. So we're now having a softer edge to our density volume, and we're at the mercy of the viewport right now, but that's essentially what we have here. Some other things we can do here is, for instance, we can put a clamp in here, so we can make sure that any values above a certain threshold are clamped pretty heavily. And the minimum, remember, at this point in time, before the negate, we're still dealing with values that we're interested in that are going to be negative. So let's set this to an extraordinarily large number, one number that we know we're never going to get to. And the max value, let's set it to just something past the surface position. The surface position will be 0. But we want to be able to feather out a bit, and this will be in Houdini units, or in the units that the SDF was generated prior to any scales. So that means when we authored this with the ISO offset or with the VDB from Polygon SOP, it will have been at the space of the current object that it was at. So that's what these units are relating to. So max, let's add a little feather of 0.001 beyond the surface. So now we're eating outwards, and then we negate this, and then we do multiply. and that sort of cleans up everything little bit easier. Now, one more thing we can do is put down a fit operation and fit range, and we can put that down in here. And in this particular fit range, what we can do is just simply add some input parameters. So let's promote parameter. I could have right mouse on the node and done that just really quickly, but in this particular case we can set minimum max and minimum max. So now when we're above, we can start playing around a bit with our volumes. Again, what makes this mapping work? I mean, how is it that I was able to access the surface field, and how is this volume operation pick up density? The answer is in here. So if we go to the volume bindings, we can see here that sine, it's basically auto bind by name. And what that means is it'll look for any named volumes, density and surface, and then it will allow you to put down bind operators or parameters, or I usually use binds. You can pick them up by name and then you can work with them. So name, it works extraordinarily well. So auto bind by name, or you can manually create your own associations. Let's say you want surface, or you want to give the user the ability to, let's say you're working in a pipeline that had rman underbar surface, but inside you were using surface to pick up those fields. You can actually manually create that binding so that the artist can then say, no, I want rm underbar surface to map to surface. You could do that, but in this case we're in Houdini and we have complete control, so it's nice to keep things consistent. And we can actually change the precision of vex as well, so we're going to leave it as auto. But anyway, we got some nice values in here. So 0 to 1, and remember we're working with the fit after the negate. So now we've sort of flipped the logic in that all the values that we care about that are inside the density with the SDF are now positive. And then we're in here, so we can actually change the minimum and maximum as we're going in. And also what's going to have a greater effect is the output. So here we can say, we can actually change the density of the output that we're doing the volumes on, and we're doing the multiply in there. So we can actually map some pretty interesting values there. And so we're going to have the values are going to have to be pretty large though. So before we start seeing a change, and let's change that. So you can see here, and I have a mouse up. That's interesting. I must have saved that update inside of Houdini. But anyway, now we can see that as we change these particular values, you can sort of change these ranges. By the way, if you want to remap these ranges on the parameters and you're unaware of it, the only way you can do it is you right mouse on the operator and you say go to parameters, edit parameter interface, because we don't have a digital asset, we just have a stock Houdini node. Edit parameter interface, go in here, and you can see you can select these parameters that were auto bound, but you can also go down inside the VOP and change this as well. But you know, maybe we're lazy and we want to change the range, so maybe you want to change the range here to 20 on the max, and you press accept. And I just did something really lousy UI wise, where this is the only one that goes beyond 1, where all the other ones are. And you can see here we can control the softness of that edge. So tons and tons of control over the volume shaping now available to us, just by knowing a few simple operations. These operations, by the way, are fully supported inside of Vex for doing volume shading at render time as well. It's fair game to put this inside of a surface shader, picking up volumes by name as well. They're all passed to you nicely via mantra and karma to do any sort of volume manipulation at render time. Now, what about default attributes? We're going to start talking a bit about default attributes. And one of them, default attributes that are available to us in Mantra, and which is not so much a Mantra, but is an adopted standard inside of Houdini, is CD. And what we want to do now is create some colored volumes inside of the volume VOP. Oh, by the way, let's see if this actually works. So if I change this to the VDB from polygons, the surface field is getting in the way. So we can see if we can turn the VDB volume off, or in this particular case, we can literally blast. Once we're done with the surface field, we can literally blast that away after the volume VOP. So let's do that. And again, blast works via by name, so we can just blow away the surface data, and then we're left with the density data. So hopefully we get the same result whether or not we're working with pretty close, whether we're working with VDB grids or with regular volumes as well. They'll both work by name, by the way, as long as you have your name set up. Now, we want to add color. So how do you do and work with color inside of volumes? It's not as easy as just adding a CD attribute inside of a wrangle. You literally have to build those volume, those color volumes for you. So let's pick on the density, because it might be easier to lift 3 volumes based on density into color. So the way you do that is you can use a merge operator, and you can literally wire in 3 inputs. By the way, the VDB side is really easy to do this, but in the regular volumes you can merge that volume 3. So now we've got 3 volumes called density, and now you can use the name SOP. This was one of the early uses of the name. It literally is also used for naming volumes. And what we can do now is we need to name our volumes cd.r, cd.g, and cd.b. And in the documentation for working with volumes, it clearly states that if you can build your volumes in such a way, they'll actually be treated as a vector inside of the volume VOP, so a vector of color. So let's do that. So we want to do 3 renamings. So we want to do group renamings, so let's 2 and 3. And if we press our name, the problem we have is here in the name above it, they've got 3 fields called density, but we have a unique identifier of 0, 1, and 2. Because we're doing this, we don't care what order they're in. So let's put group 0, group 1, and group 2. And now all we need to do in here is put cd.r for red, cd.g for green, and cd.b for blue. So now we have 3 named volumes, CD, R, G, and B, and we can merge them in as well. So now we've created 3 volumes that we can write color data to. So let's go to the volume VOP, and pretty easy. We're going to put down a bind export over here. And to bind export, we're just going to say CD. That's all we need to do. And remember the golden rule: whenever we're dealing with VOPs or VEX, you have to get both the name and the type correct. And this is, we can choose any vector type. It would make sense to set this to a vector of type color, because then it gets all the nice UI hints that this is a specific color. And we could color this red, for instance, and we see nothing in the viewport. And we'll get to that in a minute. But what we want to do now is we can add some anti-alias noise. And we're going to use position to drive the flow, to drive the noise. And let's multiply it by, we'll take the noise and we're going to multiply it by the density. Or we can reverse those, it doesn't really matter. And then actually the flow noise, let's actually make it 3D in, 3D out, because we want it to be color. Let's just add some random values to the color. And then the product, we can now author that into the bind. And the way the bind export works is that any attribute, any value that's being wired into it will be promoted up to CD. So let's see if this works. The problem we have now is how to visualize this. So one of the things we could do is put down a blast and isolate each of those color volumes in turn to inspect them. It doesn't quite make sense. You think, well, I just want to see colors. And so in this particular case, we can delete non-selected. So depending on how we're building this, we'll be able to see different things as well. So and we probably want to change that color value a lot more to actually see this as it changes. It would also help if I wired the blast after the volume VOP operation, so we can actually see the randomness in the volume. And there we go. So now we can see how we can see the red, and we can see the G, and we can see B. So we can actually see our 3 fields. But how, again, do we visualize these? A couple ways. So we got rid of our surface field, and we still got our density field in there. So let's put down a volume visualization. So volume visualization is a way of authoring volume data to the viewport so that we can actually see what it is we're working on. So the viewport doesn't know how to interpret CD on some primitives and visualize them. So the first thing we want to do is for the density field, let's choose density. And for the diffuse field, this is where it gets interesting. We can choose a CDR. And we can CDB or CDG or CDB, but there's a sneaky little convention in that if you use an asterisk, you can actually choose your colors as your diffuse field. Now, why is this singular and not diffuse field versus diffuse fields? We're not going to go there, but diffuse field can take multiple fields to derive the color. And we'll notice here that the color is a little bit bland. So we can go into the volume VOP in here. We can actually multiply by constant. So we can actually promote a parameter in here. And the parameter, let's call this color amp or color magnitude. And let's label it color mag. And now we can scale this from 0 to 1. We can do the float range. I should have done that on the other ones, but you can actually set that to 10. And so now when we go up, what this does is it tells the UI that this is the default value, and this is the range to build once we go up. And here we got the color magnitude, so now we can scale that color up. We can also scale the density that's being multiplied by it, but in this case I want to keep the density the same. We could have a separate control for density as well. It's up to you now, fully knowing that you can now create any number of volumes with any name. So that means it's up to you to define what names are going to be picked up by your shaders or the volume visualizations. Now, to cap this off, we want to actually start building a material. So I'm going to put down a material net, and let's use this volume data called CD to help color our volumes. So how do you do that? The answer is, let's go in here, and I'm going to open up the tools. I always like these tools. You know, many times tab key is not for discovery, really. It's for, even though you try using it for discovery, you know, you start tabbing, typing different names like volume, or you know, let's do max, or it's great for just pecking away and quickly getting it to a subset of the operators that you want. But this tools menu actually gives you the lazy way or a very persistent way of working with these various different operators that are in there. So the one that I'm interested in is everything that has to do with volumes. You'll notice that we actually have some nice, in the galleries, we have some nice delineations up in the top. So if I go to volume here, this is where we collected all of our volume shaders when we're authoring materials. And let's just put down a basic smoke. Nothing too special. And before we go any further, let's go up one directory and let's assign this material with material operator to our actual geometry primitives. And again, in the material attribute, let's assign it, and it's basically, I can go over here, by the way, in my tree view, and I can grab basic smoke right up here in the upper left, and then drag that into my material. And now I'm assigning material to all of this piece, all of these pieces of geometry as well. So back into the material net, you know, basic smoke. Let's see what's happening here. So if we open up general and we select this operator, we'll notice that it's already designed the architect of this particular shader, you know, way back. We've decided that going all the way back to prisms, that capital C under D, like upper lower CD, is how we're going to denote color. It's before my time. And so we'll notice here that this particular shader has tint smoke color with CD. And that's exactly what's happening here. But what is CD? Whether or not it's primitive geometry with points, or if you supply 3 volumes that are called CD.RGB, they'll be used as a vector. And it works in shaders. I said it works. So let's actually do a quick mantra render here. And let's see what this looks like. And hopefully we'll get nice rendered color volumes as well. And yes, we do. And so that means that CD, anything we do with the CD volumes here will show up in this material. If we had temperature, we could use temperature mapped into a material. If we had heat, fire, flame front, whatever volume that we have, we can now pick it up easily, both in a volume VOP and also in a material net for actually doing rendering of colored volumes. So a little bit more houseworking, all based on name. So it's all using the name attribute to identify volumes by name to be used inside of materials and materials, and it makes it very easy to work that way. I want to digress a bit and start taking a look at a lot of these default attributes that some users that are newish to Houdini, or those that are moving from one part of Houdini, let's say you've been in Vellum for a while, you know, want to move over to doing maybe some hair, and you're using default tools and you want to get down a little bit deeper than what you're normally used to. So let's take a look at the default attributes inside of Houdini and see how they play in a regular world. So if we put down a grid, and this specific grid, we can do some pretty interesting things with this grid. First of all, we can scatter points on this, if we dive inside, that is, and we can scatter some points. And Mantra, as well as a lot of other renderers, especially Mantra, uses attributes on the geometry to control how the geometry is actually created at render time. It's a render time procedural, as we know. So if we fire up here and we put a preview render across a part of our scene, we're actually going to see spheres being rendered. That's because the object above us is got some parameters on it, whether they're exposed or hidden, that tells Mantra that, oh, when I see a point, when I'm looking at all the geometry, I hit the bounding box for this particular object called grid 1, and then it appears inside of it and it says, oh geez, there's points in here. It then goes, okay, I'm now going to run a point procedural because I've been told to do that. Now what type of procedural do I run? It says, okay, put sphere disk primitives on there, interpolated normals or not, and what radius to use. Exactly. So we've created a whole bunch of default attributes that play nice with the various different pieces of geometry. And the way to get at this is we can do this before or after. And this is the nice thing about working with a procedural at render time, or a procedural in the viewport, is as long as we satisfy the last node in the chain has all the attributes required to drive the visualization, you'll get exactly what it is that you want. So there's no need to actually rasterize the geometry in here. Visualizations these days in the viewport, as well as Mantra, are pretty good. As we know, PEC primitives fall between the cracks for now, but yeah, so it's everything else is pretty much visualized in the viewport. We can actually see that on the points, though, we're not seeing that. But there is a way in the viewport to, if we go under geometry, there is a way that we can actually visualize the points as sprites, point size as well, and we can actually say pixels, lines, and disks. So there is a way of pre-visualizing this in the viewport if we wanted to. Convention is to leave it to points or pixels. If we're dealing with less than 10 million points, yeah, I use points, but if you're dealing with particle fluids where you need the ultimate performance, you can set that to pixels if you so wish. We'll leave it at points. So there is a way to actually visualize this in the viewport if you want. But anyway, scatter. So how do we manipulate these sizes? Well, I'm old school, so I'm going to put down a point operator. Even though the old point SOP is hidden for quite a number of releases, we do have a new standard of at least getting to see what are some of the default attributes available to us. Discovery is always an issue when you're first new to Houdini, so if you put down an attribute expression node or point, which is old school, you'll see here in the attribute that we wish to create under the Vex expressions tab, you can actually see that we have position, velocity, force, color, alpha, normal, texture, mass, and p-scale. P-scale stands for particle scale. Particle scale is all about instancing and dealing with that Mantra procedural as to what size it is. So that's what the P stands for. So we want to do P-scale. Now some of these, as we saw CD, basically are set up on the shader side. You know, shaders have that option that internally they will pick up CD if it exists. Velocity is used in the render engine for doing motion blur by default. Position obviously is everything. You need to have a position in order to know where to render things and to build your geometry from. And of course, alpha, capital A. Yeah, we'll get into that in a second. But then there's normal. Normal, again, is the surface property used for shading. So it's an intrinsic piece of the geometry. And if it's not there, it's usually constructed by the shader the shader author will build that for you. And then there's texture UV, which is identified, which is created on the geometry and passed into the render engine to index any texture maps. Then there's mass and p-scale. Mass is used for simulation. Old school, the old Spring SOP used to have the mass on there, and of course mass is adopted by now all of our modern solvers. And then p-scale is which we want. And we can see that if we set p-scale to self, it initializes p-scale to 0. And sure enough, there's 0. So we have a whole bunch of different options in here that allow us to initialize this as we so wish. So we can initialize this to a constant value. So we can set a constant value. You can see very quickly we're passing this all to Mantra or to Karma or to whatever render engine is currently hooked up to Houdini. If it supports the spec that we have, then you can see here you get your spheres rendered. And we can also add a little bit of UI in here. You can say multiply by a constant value or add a constant value. And that allows us to take an input value and do it as well. There's also some really nice options in here to random scale a value. So you can create random sets and you can change your constant value as well here. So you can initialize all your p-scale values very quickly here. The scatter also does this internally. So if I put the display flag on the scatter, if we go to output attributes, we now have p-scale here as well. So it actually output an attribute called p-scale by name. And you can see here it lifts it as well. There are some other attributes in there that we can have a look at. But this also works for instancing as well. So let's say I have my scatter on there, and now I want to put down, instead of spheres, let's put down a box, and let's add vertex normals, and let's make this box unit size 1 by 1 by 1, and let's actually do a copy to points. And this is as old as the hills. So what's happening here is the copy to points will inherit to p-scale and add it to our boxes. And our boxes are now being scaled. The copy to points is taking that box at its original size, and then there's also a p-scale attribute present on those points that allow us to actually see all of that data. And the copy to points will use these template attributes to render the boxes with. And we can control how those attributes are used internally by the copy operator when it does its instancing. Now, one of the things we can do here is the box operator is just some plain old geometry, but the copy to points actually has some really interesting logic in that it does a pack an instance, and what that will do is it'll try to look to see in the input pieces of geometry which ones are the same geometry and aggressively pack them. So instead of having hundreds of unique pieces of geometry, it now has a single box defining all of these packed geos, so that gets very, very efficient to work with. So one of the things we can now do is do an attribute. We have these new operators, attribute adjust, and let's say we want to attribute adjust a float, in this case p-scale. Now the attribute adjust nodes are just great, and as I said in the Houdini 18.5 release, it would be really nice if there was a specific one for color. So fingers crossed that will be coming in the next release. But in this particular case, we'll soldier on with what we got. So we can actually take the attribute name. It's already set up for p-scale, because why not choose a default? It would be p-scale. You can choose all the other attributes that are available to us. And the copy to points doesn't have p-scale. So it would make sense to put this up here. And or we can put that down, we just put that above here, and order of operations. So now you can see here's p-scale, and we have some randomized values on there, or we have some values on there. So we can adjust that with a constant, or we can do random, or we can do noise. So let's do some noise on there, and a min and max value. So now we're controlling p-scale after, or before or after the copy operator. If we actually went to the copy to points and we mapped those attributes over, then it would work as well after the copy to points as well. But here's the attribute adjust float. So we can now see the spheres, or we can actually display the copy to points. We can actually see our boxes changing in random size as well. And yeah, so that's one of them. There's another one as well. So if we put down, let's put down an attribute point expression in here as well. And there's a few others that we can add that are custom, that are actually known as well. There is p-scale, but there's also scale, which is a vector 3 version of p-scale. And it's of type vector as opposed to type float. And here we can actually set this, we can basically set it to add constant value. And we can now add specific values to that as well. And it'll actually get picked up in the render engine as well. And let's kill the renderer for now. And so that means that we can do anisotropic scales on all of our primitives. And we're going to have a tour of MOPs in a bit, and MOPs abuses these attributes, and it also uses an orient attribute to determine how these pieces all fit together. But we're already starting to do some pretty cool, what you would consider to be motion graphics type work, where we could animate all these things and control at the render engine. And because we're working with packed primitives, it's very, very fast. Very, very fast way to work. Now I want to open up another file that I've already prepared that covers a lot of the default attributes, which is a great file to have a look at. I will make these available. But we can see here, let's turn off the tools for now. So we saw our simple grid example where we're doing, take a grid. Some of the default attributes we have also is color, CD, and alpha. This is before my time. So why capital A alpha, why capital C CD, and why is that the standard feeding into our shaders? Not my call, but I've been using them for so long, they're just part of my language. So it's just one of those things that the quirks of Houdini, all software have quirks. And that's just one of the quirks of Houdini. And I like it. I really do like it. It sort of harks back to RenderMan shaders, CI for color initial, and CF for color final, and all of those things. It fits, and I like CD because it's a generalized version of that. And we can have adjust attribute vector. So there's some really cool attribute adjust vector. We saw attribute adjust float, and we can choose different types of Manhattan, cellular, revised, simplex, Ferlin flow. So if you're into motion graphics, MoGraph type work, there's some really cool noises in here. And as we know, noises are everything, and you can use offsets on the noises. You can change the element size. You can modulate this other noises. You can add fractal types. You can add roughness if you want. A whole bunch of different options. Attribute adjust vector is just a super powerful operator for dealing with even color as well. It doesn't have specific color operations, like there's no lookup ramps or all of that, but you can build that in yourself for now. And of course, this is all feeding into the material. And as I said before, what makes this all go is there's a basic material in here where you have CD and alpha feeding into the PBR diffuse compute lighting and then into my material. So this is the genesis. So you're saying, well, can I change CD and I can change alpha? And the answer is sure. You can do that. You're just going to be fighting 25, 30 plus years of using CD and alpha in all of these shaders. So all of these shaders by default have this logic built in where we have CD and alpha by name. And if we take a look here, you can say use point color. That implicitly means it will be using CD. And we even give you tint color with CD attributes. And opacity is going to be set up to using point alpha as well. So if you need to have a reminder as to how to name these attributes, go to the material. That's where they're used for specifically for color and alpha. And all of the volume data as well for volume attributes by name. And here's another thing really interesting. We can start off with Louise and we can pack him. When we're dealing with instancing, direction is everything. So if we want to aim Louise down the Z direction, we need to work on that. So in many cases, instancing is always down the Z axis. So if we wanted to have walking Louises, we could, and usually it's rotate X by 90 or minus 90, depending how it is. And we can have Louises facing forward. And over here, I show you how you can take a grid, scatter some points on it, and use an attribute wrangle. And a lot of these tools use element num, and then we can use an attribute expression in here, which basically does scale. So we have p-scale, scale, and a normal. And you can see here we're adjusting the normals as well down the Z direction. Normals almost always face down the Z direction as a local axis. And then we randomize, attribute randomize, we're randomizing up. And up is the up vector that we use to orient instances, as opposed to using the orient quaternion to do all of that. So the copy to points, as I said, uses these attributes, and depending on whether or not we want to point Louise facing down the Z direction or aiming down the Z direction, we can do that as well. And so pretty straightforward. And of course, if we go to the attribute randomize, we can change any of these parameters as well. So under the attribute expression, yeah, where is it? Pardon me, attribute randomize up. So yeah, so it does a randomized value for us here, and we can change the default global scale of this attribute. Yeah, and options in there. So yeah, we can do some really cool stuff there. And then we have a point expression in here, and these are all packed primitives, by the way, by name. Speaking of that, if we go to name, let's see what I call it. Path, there is no name, I should have named it. But there's an attribute randomize down in here as well. So we can post randomize a lot of these attributes, including CD, so, or we can attribute adjust the vector as well at any point in time, and then apply our material and render, and do a whole bunch of work. And finally over here, wires. So Houdini can render points. It can also render open curves. So here I got a grid, and it's just set to rows, and I can adjust the width attribute here. And width is one of those things that is not supported in the view, or yeah, it is supported in the viewport. I just had to go up to the object level and turn it to turn on curve rendering and to use the width. But width attribute is a float that determines the width of the ribbons. And here's a simple example of using orient as well, but old school orient, which is just a vector direction, which shows you how you can, you know, twist that vector. So here I'm using an attribute in the orient along curve. Orient along curve is really cool because it allows us to create attributes that wind along different things. And I'll show you what's happening here. If I turn on the up vector and I kill the render, you should be able to see that up vector in the viewport, or the width attribute. And there's the up vector. So you can control the winding down here and the number of twists. So if you need to twist telephone cords or do all those sorts of types of operations, orientation along curve, which is a new operation, really helps out with that. And again, so let's turn that off. And so let's turn width off as well. And of course, rendering is the only way to see this stuff, the orient, I believe. And then, of course, we can put point expressions, put colors on them, and render them as well. The nice thing about these ribbons, though, is they have UVs on them. So that means if you were assigning material to these ribbons, in this case, I've got mandrels on them. Let's actually make this a bit brighter. So if you go into here and you say memory toolbar, or probably not the memory toolbar, the correction, not that, correction toolbar. And let's get rid of the memory. Don't want the memory toolbar. And we can now make this a lot brighter. We can increase the brightness as well, so we can actually see some things in the viewport. You got color spaces in here and everything. If you didn't know that was in there, it's tucked away right there in the correction toolbar. You can actually control color space of the viewport as well. And there you go. So you can even assign mandrels to these ribbons. So points and curves are fair game. And the fur tools use this a lot in the fur procedural inside of Mantra. Now, as tool architects, it's really nice to see how other third-party tools are implemented inside of Houdini. So the next little while, I want to take a look at MOPs really quickly. So let's put down some geometry, dive inside, and I have the MOPs tools installed. Please go to the website and see how to install it. It's pretty easy with packages these days. And I'm just using the freely available version of MOPs. There's also a paid-for version as well. And I'm using the tool gallery again. I'm going to expand all of it so we can see that MOPs is into 4 different categories. What you need to know about MOPs is everything, most everything starts off with the MOPs instancer. So we put that down and we feed in any geometry we want. We might as well stop with a box. And let's turn on add vertex normals and wire that into the MOPs instancer. And we can see that if we turn on smooth wire shaded, we can change the size of the incoming boxes here if we wanted to. And then you can see them here. Let's start with 0.1. Let's get them close. And then we can go to the MOPs instancer, and here we can also scale them as well. So this is a suite of tools that use really just like all the default attributes we've been looking at for the last little while. Plus it brings a couple of its own, which are really sweet. And it allows us to build these tools. And essentially it works entirely with packed geometry. So all the tools, it it can work with raw geometry as well, but when you're using it in MoGraph style with the tools as defaults, it packs all the geometry. And as we know, packed geometries work with all these procedural attributes that pass into mantra and then do really cool things. So it allows us a lot of freedom to do these all kinds of really cool things. So the first thing you want to do in MOPs is, he sort of works opposite the way that you're used to using in Houdini, but it works the same way that you're used to using for MoGraph operations and other applications, in that you add modifiers after the fact. So in this case, we can add noise falloff, for instance. There's all kinds of these falloff type tools, and that's where the brilliance is. So we can add a noise falloff, and we can see here. And let's add a lot more points to this. So we can go under distribution, and we can change the size of the grid that we want it to. I don't want to create a volume type operator. I just want to do the X and Y on the plane. So I just did a really quick, I just double clicked on that and dragged it drop over to there to create a relative reference. And now I can create a huge grid here of boxes. And you can actually, under instancing, you can actually open up here. You can go to options, and for each of the pieces coming in, you can do some tweaking on here. There's a uniform scale, and guess what? It's affecting scale and p-scale, which we had a brief look at earlier. So if you want to basically just take a look at, there's p-scale, and then there's also scale. So it's using all of these default attributes that we talked about before, plus it's adding a couple of its own, MOPs falloff and MOPs index. So MOPs index allows us to index into all of the various different primitives that we have, and as well MOPs falloff, which is built by these falloffs tools. So there's noise falloff, and the other one I'm going to do, let's do a shape falloff. And so the whole idea here is we add all of these different falloff operators, and if we hit enter in here, and we can actually visualize these, preview the falloff here, and we can actually change the type of falloff that we have. Let's sort of spherical, and in here we can change the inner radius and then the outer radius, and then we can add some noise in here as well. So noise is awesome, and we can add some noise. We can change the frequency of the noise, increasing it, decreasing it, and we can add octaves, add roughness to the octaves, and even make it time varying. So if you make it time varying, you can actually see it animate, and we can do the same thing for the MOPs noise falloff. Preview the falloff, and we can choose all kinds of different types of noises. Let's choose something pretty, let's choose simplex, and make it time varying as well, and we can change the amplitude if we want, and we can change the frequency as well. So let's leave that as well. Now there's a combiner. So it's common to combine the falloffs, and that way you can control how they mix together. And again, it's using this MOPs falloff attribute. So just like we saw before, they're creating their own set of default attributes, and they stick to them. So there's MOPs falloff and MOPs index alongside all the other default attributes that are available to us in Houdini, and they do the falloff, and you can combine the two. You can add them, you can multiply them, or you can subtract them, or you can overlay. So there's a whole bunch of different options that we can do. We can preview the falloff here. And we can probably turn the, and here we can see there's overlay. We can actually do an add, we can do a subtract, and let's do a multiply. And now how to do work. So now that we're doing now that we've created our masks, now you can actually do work to those packed primitives. And one of the pieces of work that we can use is a transform modifier. So under the modifiers, there is a transform modifier right here, and that does all the transforms from scaling, rotates, and it'll implicitly use this MOPs falloff value without you even having to specify it. You can see the falloff attribute is defaulting to MOPs falloff in the parameters themselves. And here we can change the way it happens. So we can actually scale in Y. And we're actually changing those default attributes. There's p-scale and then there's scale. So we're actually affecting scale. Which is where over here somewhere. Yeah, there's a scale attribute that we're affecting as well. And uniform scale is actually affecting that p-scale as well. Now we can do this anisotropically as well. So we can actually make them go flatter, make them go very flat, like flat paddles, and then we can make them long and narrow depending on how they do. And then we can also rotate them up in the X direction if we wanted to as they play forward. And now we can see that the pieces are scaling and translating, and now we can translate them up in Y depending on how it is that they're working. And so we can make them a lot wider, so we can actually create these paddles flipping if we wanted to. And that's the beginning of MOPs. Now, another thing you can do though is, we can now augment this as well. So MOPs gets you most of the way there, but if we wanted to render this in an interesting way, let's say we wanted to create alpha from that MOPs falloff value to go along with everything else, we can just put down a wrangle. And in here, so we can augment that, note there's an attribute called MOPs falloff. We can put it here f at alpha, because we now know what alpha is, and f at, and it's going to be MOPs underbar falloff. And we close that, and now all we need to do is just put down a material network, while that in, and put down a material network. And let's just put down a principal shader, and let's go up here and let's just assign that principal shader to here, and it's under material net principal shader. And if just to make sure, let's dive inside of the material, select it, and let's go under opacity, and it says used alpha. I believe because we're dealing with packed primitives, you need to select this option here called use packed alpha. And for the surface, use packed color. So there's the only two things you need to be wary of when you're dealing with packed primitives with MOPs, is unless you unpack it and then you lose your efficiency. And the base color, let's make it a bit brighter. And let's take away some of the reflectivity in here, and let's increase the roughness. And let's display the material. And actually, we can actually boost the albedo multiplier if we wanted to. And let's go up to the very top, and let's just add a skylight, or an environment, or let's add a skylight. And dive inside of here, and let's just quickly create a simple render region to see our work. And that's pretty much how you get started inside of MOPs. We can see our alpha being picked up. And we can control all of those options. We can remap alpha as well, so it doesn't show up quite as dark. You can go into the MOPs and change all those values as well. So hi, it's Jeff Wagner. I had the pleasure of interviewing Henry Foster today, lead developer on MOPs, the tools that allow you to do motion graphics inside of Houdini. And in the discussion of the Illume that we're dealing with this time out, it has to do with everything and anything to do with working with attributes, making things easier inside of Houdini, and how that applies to the great tools that Henry and what Moritz has started, and Henry's continued on the great development of this tool set. So anything you want to say about yourself, introducing how you got into this industry and how you got inspired into motion graphics?
Sure. So I started way back in 2006 as a sort of just a 3D generalist, freelancing in LA. And a lot of the shops that I worked at, even though I wasn't really a motion designer myself, I was a 3D generalist, and so I was working at tiny motion design shops that needed to get a lot of graphics out in a hurry. They didn't have many resources. The deadlines were really short because it was usually for commercials. And so there was always this rush to get things out the door quickly. You had no time to really sit down and really think about how to approach a problem. You just had to do it. And so as part of that painful process of learning how to be quick and adaptable like that in 3D, I started teaching myself scripting. So first Mel, because I was a Maya artist, and then Python. And then I quickly started building tools for myself to speed up that process. And that eventually became sort of working as a 3D generalist / pipeline guy, where I would build pipelines at these motion design studios that never had one or didn't know what pipeline was. And it wasn't anything nearly as complicated as what you'd find at a movie studio, but it was just like being able to consistently know where your stuff goes, how to get data into and out of scenes, just like, consistency and pulling data out. So, but after years of working as both an artist and a tools developer, just for my own sake and for the sake of small studios around LA, MOPs kind of honestly popped up as kind of a dare. I was on Discord in various Houdini Discords, and someone had brought up that it was so hard to do in Houdini what was so simple to do in something like Cinema 4D's MoGraph or Maya's Mash. And people kept wondering, like, why is it so tricky to do these things? Like, it didn't make sense to them. And, I knew, just sort of thinking about it, like, well, of course Houdini can do this. Why couldn't it? It's like Houdini's core toolkit, the whole API underlying everything is so powerful that, like, yeah, of course it could do it. It can do anything. And then I actually sat down of doing the work of trying to translate first Mash, because I was more familiar with Maya than Cinema, trying to translate that. And I really quickly realized, like, oh, there's a lot of math here that I don't know. So I had to sit down and kind of relearn linear algebra, and how transform matrices work under the hood, and then quaternions and all this other stuff that I hadn't really thought about since high school. And then sort of partway through that process, Moritz, I don't know how he found out that I was working on it. He must have seen me talking about it with this other guy online, and he reached out to me and asked if I wanted to jump on. And so we sort of both took a look at each other's respective toolkits and then found a way to kind of combine them into one, and that's what became MOPs.
So Henry, what is MOPs and what audience is it geared for? And as well, is it free, or do you actually have to pay for these tools?
MOPs is a toolkit for motion graphics in Houdini, but it's also a tool for handling transformations and other things that are sometimes difficult to think about in 3D in general if you don't have it abstracted away. There's a lot of math involved. So it's a way of achieving gestural animation in Houdini, where you can just think, I want this group of things to kind of move in this direction or aim this way and by this much. And so it's very gestural. You don't have to think so much about it. And so you can get really complex animation out of just a few broad brush strokes. So it's great for getting complex behavior out of just a few simple keyframes. MOPs itself is free. It's open source. It's free. You can get it on GitHub, and it always will be open source. There is a paid add-on called MOPs Plus that I released at the end of last year that is a little bit more focused on simulation tools. So some of the new tools are geared towards being able to art direct simulations the same way that you would art direct things in regular MOPs. And there's also just a few new tools in general to try to help add things like typography to Houdini, so like a more robust tool for dealing with type. And a handful of other just like workflows in Houdini that can sometimes be a little bit tricky, and I'm just trying to smooth them over. It's designed for motion designers who are trying to transition into Houdini. That's a big part of the audience. But I don't want to write it off as being strictly a motion design tool. There's a lot of stuff that you can do with the MOPs tools that are geared towards things that effects artists would typically want. And in previous presentations, like the Hive presentation I did last year, I showed a couple of examples of being able to sort of manipulate rigid body simulations after the fact, because you have access to the local transforms. You can quickly make adjustments or match transforms to each other, things that effects artists would have to deal with pretty frequently. So it's as always, it's a fine balance, but it's trying to make these things accessible to new users or users in Houdini who are less technical, but without making it useless to the technical artists. It's still following the same rules that the rest of Houdini follows. And most nodes have the ability for you to jump in and write expressions and overwrite things. So advanced users should feel plenty comfortable just overwriting things to get exactly the effect they want. So
this opens up the door now to comparisons. How how does it compare to C4D and MASH as motion graphics tool sets go?
So the gestural system is going to seem really familiar to users of both. The idea where you define a transformation and then you define how much of that transformation you want to apply, and then the system does the rest of the work is consistent for both. I come from a Maya background. I actually don't know Cinema 4D at all. So it's hard for me to make one-to-one comparisons. But from past experience with Moritz, who is more the cinema guy than me, and from talking to cinema artists over time who are trying to transition into Houdini, the overall workflow should feel pretty familiar in terms of how you manipulate geometry, how you decide on the weight of a transformation, that sort of thing. Just as a aside, I don't want people to think that MOPs is only limited to those things, though. There's a lot of stuff that MOPs does under the hood that can be used in, thanks to how open Houdini's framework is in general. There's always interesting ways that you can apply these things that are not just for motion graphics, that are not just for the kinds of things that you would see done in MASH or MoGraph. MOPs can do a lot of other weird stuff that you normally wouldn't see in those tools.
Well, that sounds amazing. I mean, that sounds to me like a tool of opportunity. When I started using MOPs, for me, I almost had a tear to my eye because I go all the way back to prisons. I'm used to writing. I was famous for writing these point expressions in the old point SOP that were basically like an entire book to do really awesome things. But when it came time to actually teach that, it's very challenging. So just seeing the way that MOPs handles all of these default attributes, as you said, you had to roll up your sleeves and learn the basics of linear algebra in order to get a grips of that. But I do believe that it's such a great encapsulation of all of the standard workflows that you have inside of motion graphics. But also, it's interesting. Embracing simulation in the MOP tools. How tricky is that? Bringing in simulation into motion graphics, because the most daring I would get in the past was using a spring SOP.
Yeah, well, we even before Moritz left the project, we both knew that we wanted to try and hit simulation at some point. We just weren't really sure how we were going to do it or what that was even going to look like. And with the open source version of MOPs, the most common ask that I got from people when people would actually reach out and say like, oh, how do I do this? How do I do that? Was they wanted to know how to get their instances to collide or at least not penetrate each other while they moved. And I kept trying to explain like, look, there's nothing you can do unless you run this as a simulation. Like, MOPs is procedural. You can't really get accurate collisions that are going to have continuity from frame to frame. Like we could detangle them on a single frame, but that then you're going to get all kinds of jittery movement during the actual animation. So that eventually became a lot of research into figuring out how to take what MOPs does at the SOP level, and as far as like setting a goal and weighting that goal for transforms, and turning that into something that can be used in simulation. So it couldn't just move things; it had to be able to move things in a way that Houdini's internal solvers would be comfortable with. So it turned into sort of a DOP version of apply attributes that actually computes the forces necessary to get to the goal that you want. And so then that became sort of the central part of the toolkit, in addition to all of the fall-off nodes that people are already familiar with if they've used MOPs. It was sort of a way of like, well, how can we make it so that people can art direct rigid body or vellum or pop simulations the same way that they would art direct something in SOPs, where you just say, I want you to go here, and it just figures out the rest for you. So it's still a bit more complicated than that, and there's a lot of little gotchas and things that are just inescapable in simulation because there's so many variables you have to worry about. But that's sort of the initial vision, and that's still the goal as I continue to refine this thing based on user feedback.
So that's the part that sort of was really interesting. As I was using the more recent versions, all of a sudden I say, oh, if I do advection, I'm doing simulation. So nice choice of words to sort of not to scare the users too much, right? when they're getting into it. So, but now you're on the slippery slope of simulation, right? And right now it's mainly packed primitive. As we know, the theory of MOPs is you've got a really great presentation, by the way. If nobody's seen it at the last Illume last year, you gave a great introduction into what MOPs is. It's essentially
that was
working
Hive.
on oh, the Hive, that's right,
Yeah.
the Hive. And you're working on packed primitives. And, but, you know, the question that always leads to is, what about volumes? Yeah.
That is a good question. I can say that volumes of some kind are in the works. It's something that I'm trying to draw battle plans for in terms of how to get, you know, how to make volume advection of particles in rigid bodies. You know, when you're talking about volume velocities and things like that, getting things to orient to the volume field a little bit better. You know, there's like simplistic ways of doing that, and there's already a MOPS aim DOP that will gradually steer you towards any vector like velocity, and it has other options that kind of make it fairly straightforward to use. But there are fancier ways involving dot microsolvers that you could align things to velocity that are a bit more interesting. And as far as volume simulation as a whole, in terms, you know, pyro or flip, those are probably a long ways off in terms of what we can do with them in the MOPS workflow so far, but I am really interested in figuring out how to take the simplicity of things like falloffs and apply that somehow as a way of quickly generating things like control and mask fields, because those can be a huge influence on how you build a simulation. And sometimes the way that you need to construct, for example, dealing with pressure fields and using those, that's a common way to mask something to avoid mushrooms in a pyrosim. Figuring out better ways to generate and modify that pressure field for use as a mask, I think, is like a, you know, mid to long-term future goal for MOPS.
Yeah, I can easily see, because as I was using the latest version, you're starting to get in simulation. I'm going, oh my gosh, imagine if we could use volumes to also influence, like if you could somehow, in your clever way, that because MOPS is just clever every which way you slice it. It just makes these workflows quite elegant and also layerable and also stackable. And being able to do that is great. Again, another question on keeping up with the advancements inside of Houdini. 18.5 has KineFX now, and it introduces the ability to take these backbone spline curves and now to apply really cool transforms to them, but still keeping in a more kinematic way. Has that sort of piqued your interest?
Oh yeah, I mean, KineFX is incredibly fun. When it was first released, I did a bunch of R&D on it, trying to figure out how I could tie my system into it. And to a limited degree, I've already got that working. I mean, MOPS nodes will write and read the transform attribute, the same one that KineFX uses for world space transformations. And it can create some pretty fun results as far as being able to use MOPS to manipulate KineFX rigs. The problem is that because 18.5 is so new and I've got a lot of users that are still stuck in 18, what I don't want to do is have to fork MOPS into the KineFX supported version and the not KineFX supported version. So my hands are tied a little bit. Like, I want to wait until KineFX is a little bit, has just been around a little bit longer. And then, yeah, absolutely. I want to be able to use MOPS nodes in a way that you can do all of these fancy procedural transformations on KineFX skeletons in their own local space, which I think could be really powerful. Those tools are, I mean, all the stuff that's been introduced in 18.5, it's like kind of overwhelming. Side effects is working so fast, and there's just so many new toys to play with. So it's a perpetual challenge to try and keep up with you guys. But it's fun. I really want the tools that I'm building to feel like they're part of Houdini's native tool set. And that does mean that I have to just get all these systems talking to each other one way or the other.
Yeah, well, it's really nice because they're a really tight ecosystem, and using the MOPS underbar language to define what attributes you are working on, and the fact that you can actually use them on pretty much any Houdini geometry right now. And the even nicest part about it of all is you don't even have to worry about packing your geometry. You're doing all of that housework for the user. You can just pass in a sphere, some basic primitives, and it automatically converts them into packs and then makes them available for all of your placement tools, you know. And just to echo some of what the community has been hearing, I've been picking out a couple testimonials as I'm watching people show videos using MOPs. And one of them is that the one that struck me is that anybody who uses Houdini should definitely use MOPs. And after I've used them again, you know, I've been playing around with them again, the latest cut in the last couple of weeks, and I have to wholeheartedly agree. Even though we have the new attribute adjust, point, vertex, and vector nodes in place, they make dealing with the attributes a lot easier. But then as I was using MOPs, I'm going, I just throw it in there, and it just gives you yet another tool to sort of muck around with the attributes a bit. But you know what? I like the MOPs attribute noise better because it's a lot more visual and a lot more there. But you can intersperse the new operators with what it is we're doing as well.
So
go ahead.
So the new stuff that you guys have added in 18.5 is scatter align is long needed. I mean, that solves a lot of the same problems that MOPs transform was originally trying to solve, as far as being able to reorient things in their own local space, to twist around a normal or something like that. That's so the fact that these tools some of these things are being sort of slowly folded in at a native level, and attribute noise is brilliant. I love it. It's sort of serves a different purpose from what MOPs is doing, but they're solving the same problem in different ways, and sometimes one way is more advantageous than another. But it's fantastic to see these things as part of the vanilla Houdini toolkit.
And that leads me to my next question. When we're going into motion graphics, you know, the feedback you get, you know, how do you manage the feedback? How do you manage all the features that are coming in for MOPs, you know, given your time as a full-time artist in this industry? And you know, how do you keep this community effort going? It seems daunting in some ways. I'm wondering how you manage what new features go in and what do you work on and what do you have to push off?
Well, as far as getting feedback, that's actually been one of the hardest parts of this whole project, is that most users are silent, or too silent. And so when bugs pop up, I don't hear until a more motivated user complains. And sometimes people think that they're probably bothering me with bug reports or something like that, or they just don't feel like it's worth reaching out and saying anything. But honestly, like, when people get out there and they email me, or they post to the MOPS forums, or they complain on Discord or anywhere, like, that is the way the software gets better, because there's no way that I could ever debug this stuff completely alone. Like, I need people to discover those edge cases, to figure out when things break, or to just come up with completely novel ways of using these things that I wouldn't have thought of. You know, I'm a solo developer, and I do things one way. It's hard to predict how other people are going to use these things. So just getting people to reach out and say something when they need a new feature, or when an existing feature isn't working the way they expect, has been really difficult. But the people that have done so are one of the main reasons why MOPs can keep moving forward, is because I know what these guys are trying to do. You know, once I look at their scene files, or I know the ways that they're using the program that I wouldn't have personally thought of. And every time you chip away at those edge cases, the whole framework gets stronger. As far as managing time on, like, deciding on features, that's also been really hard, because a lot of user requests that come in are for very specific things that they want to be able to do. And it's with any system like Houdini, where you have these atomic nodes that you're trying to create more complicated structures out of, it's a really fine line to walk between trying to give the user exactly the node they want that does exactly the thing that they want, or keeping things as a framework. Because in order for these things to be discoverable, you have to have consistency. You have to have a consistent approach about the kinds of problems that you're trying to solve. And if you get too particular about things, it starts to get fragmented. And you also, you know, if a node is trying to do too much at once, you're slowing things down potentially, because in a lot of cases the user doesn't need all of that. You know, you could have 150 nodes behind a switch, and you're not even using half of them. But you're increasing the chance for error, because now the more things your node is trying to do, the more assumptions it has to make under the hood. And for me, the better way to go is to try to make as few assumptions as possible and just have one or two nodes that are doing a lot of the heavy lifting, sort of the API nodes, which is what MOPs apply attributes does, so that the rest of the nodes are just sort of using that internally, so that the only assumptions that I have to make are about a few attribute names, ID or name, and then the standard transform attributes that the copy stop uses, the template point attributes. And as long as those things are consistent, and in Houdini they almost always are, just because that's how Houdini works, most of the rest of the nodes can kind of follow. So sorry if I rambled on that a bit. It's just it's a really tough balancing act, because I want to make it easy to use this stuff, and I want people to be able to think about what they're building conceptually, rather than having to worry about math or what Houdini is thinking about under the hood. But you can't, in my mind, it's better that people think about it as a series of steps and just have to plop down a couple of nodes that by themselves are simple and make sense, rather than trying to make this one uber node that does everything for you.
Yeah, I would also argue that with motion graphics, the type of a user that is doing motion graphics is more than willing to build these really complex recipes. I just think that the barrier of having to understand matrix math and matrix transforms to get your orientations correctly aligned, when the artist just goes, just make it point in that direction, and when it moves, sensibly make it go in that direction,
Yeah,
and
it's
do all the
conceptually
housework underneath.
No, and I struggled with the same thing. It's the math honestly is hard. I still get my order of operations on quaternions wrong all the time, and I've been writing on this stuff for years now.
Yeah, that's for sure. Just one more question. Motion graphics, it's it actually has genres. I actually think it has genres now, where you have your more things that go retro, which sort of I love the retro motion graphics type work, and then of course you have the cutting edge motion graphics that's relying more and more on solvers. I love your Spring work inside of there as well, and bringing all of the advection type tools in there to sort of stay forward and all the trails. But how do you personally stay up on the latest on motion graphics?
That's a good question. I mean, part of it is just there's a lot of both of those kinds of motion graphics existing on Instagram. So people are just posting. It's honestly overwhelming how much stuff people just throw out there. I mean, the constant content stream. Just following side effects' hashtag alone is crazy. There's just people are just churning out stuff nonstop. And Houdini has been pretty good about sort of skirting that boundary of both of those categories of motion graphics that you brought up before, because like it is possible now. I mean, it always has been, but it's easier now to do a lot of these things, like the retro things that you brought up in terms of just like the simple loops that you see people do, where it's just like spheres sliding through tubes and squares and the kind of stuff that MoGraph was really famous for. That stuff is coming out of Houdini at a pretty fast clip now. But then the visual effects stuff, like what Houdini has traditionally been incredibly good at, there's tons of that content being posted too. But it's, how can I put this? Trying to do this stuff in other softwares where you're trying to do a very visually complex thing that's still abstract is tough to do in other software that is either very much like C4D, where it's sort of, it leans harder on being able to do motion graphic style animation, but it has a harder time with effects unless there are plugins that you need to get. There's X particles, things like that you have to do to make that work. Houdini has all that stuff natively.
So how does one get MOPs?
Sure. So to get MOPs, as you said, you go to the website. There's a link to GitHub, and from there you can download a zip of the latest master build. You can also there's a page on GitHub called Releases, and if you go there, you'll see the latest release all bound up, ready to go. You can just download that, and then there are installation instructions included. The packages method is by far the easiest way to go. Houdini introduced packages with a version and a half ago, maybe was it 17?
Yep.
And they are so much easier than dealing with manipulating the environment file. a lot of other plugins in the past have leaned really heavily on the environment file. And when you're trying to chain multiple plugins together, it can get extremely complicated for people who aren't used to dealing with the command line or dealing with editing text files for configuration. So I would say follow the package instructions because all you have to do is edit one file just to point to a different path and then copy it to your packages folder in Houdini, and then everything is done for you. If you're a technical user, then I assume you already more or less know how to use GitHub. And so I would recommend just using Git commands because it will make it easier for you to update later on.
And I guess the one question I also have is about MOPs Plus. How would you get into MOPs Plus? Okay,
so MOPs Plus is the paid version, and it is technically software as a service. So you pay a yearly cost for MOPs Plus, but the yearly cost is for updates. So if you don't feel like you need to update, the software is still yours forever. So you'll just be locked into the latest version released when your license expires. As far as getting it goes, if you go to the main website, the first link that you'll see in the main banner is going to be for MOPs Plus, and that links you to both the changelog if you want to see what's new, and also to the purchase link. So all you do is make an account. It just asks for email and password. You buy a license either for Indie or FX, and then you're good to go. You'll be emailed a download link. And then from then on, you can just go to the page to download whatever the latest version is that you want. And you'll have a link to all of the licenses that you've purchased, which you can use to activate. So you can, for this is important for indie users especially, you can use the same license on both your main computer and a side computer. So for people that like to bounce around and experiment, it is a node-locked license technically, but you can activate it on multiple stations, no problem.
Fantastic. So thank you very much, Henry. It's been an awesome interview, sharing a lot of things about MOPs. And I still have to say one final testimonial. Another user said MOPs is the replace the copy to points that I've been waiting for. And I couldn't agree stronger. It's a great set of tools that complements Houdini moving forward. So thank you, Henry. Thank you for the contribution of MOPs and continued support. And everybody out there, get your MOPs Plus and start diving into the world of motion graphics. And trust me when I tell you this, you don't have to wrangle anymore to do some amazing work. Thank you, Henry. Thank you.
Thanks so much, Jeff. Thanks for having me here.
You bet. Bye. Hi, I'm Jeff Wagner, and today I have the extreme pleasure of interviewing Moritz from Entagma. So Moritz, what is Entagma, and how did it begin? What was the inspiration behind it?
So everyone not knowing me, my name is Mo. I'm from Munich, Munich-based designer, 3D guy, jack of all trades. I don't know, whatever you want to call me. Used to work in advertising commercials for quite a while. Used to use another standard DCC content creation tool, which, to get into your question, I felt limited by after using it for around 5, 6, 7 years. So I was bumping into walls left and right and had to really hack it and bend it in order to get what I wanted from this tool. And to be honest, my partner in crime, Manu, he kind of pushed me towards trying out Houdini. And I was kind of resistant to it in the beginning. So he pushed me like 3 times, and twice I stopped using it immediately after a week or so because it was so weird and inaccessible to me, but kept coming back because it seemed to be the only tool capable of enabling us to deliver what we wanted back then, which was really non-standard effects, non-standard design, using and abusing more complex algorithms, more complex effects tools in commercial work, that is, or in design work, rather. So yeah, that's how we got started, or how I got started.
Motion graphics. It seems to be heading in all kinds of different directions. There's the one hand, you're balancing artist creation versus the technical aspects of the actual production. And if you follow any of the trends on Instagram, the complexity of the work now is getting such that it's requiring ever more complex tools. And how do you personally, first of all, keep on track and get inspired in this industry of motion graphics? And secondly, how do you address the growing arms race of complexity and yet still, be able to make this fun?
So let's start with the kind of quote unquote arms race of complexity. And I've been discussing this with Manu recently. And actually, when you go on Instagram, at least when you go into the kind of more modern, more contemporary artists and 3D artists, you can see 2 or 3 ways of dealing with that. And one is getting good at the tech, getting good at just doing this very intricate effects work. The other is doing kind of a happy middle ground between an abstract design, beautifully rendered, beautifully lit, with what I consider medium complex tech involved. And then there is the high concept work, which not necessarily has to be technically that brilliant, but stands out due to its concept. So those are these 3 areas that I think you can isolate nowadays on contemporary motion design, at least. And I think each one of those areas has its legitimacy. I personally feel more drawn to the technically challenging stuff. I think I would not be the right person to do high concept work. So that's what I try focusing on. And to keep up with that arms race, I think one thing that helps is to be honest with yourself that you focus on this one area. In my case, it's become more and more tech and a bit design, but less and less concept. Which, of course, on the one hand, you could argue kind of makes you a lesser all-round designer. On the other hand, it enables you to get kind of very, very good at a very specific part of the task. So that's what I'm trying to do. And the means by which I try doing that is lots of research in really arcane places and just trying to intertwine those together. I just recently got into this one algorithm, which seemed kind of weird to me, and I couldn't find a good explanation. And I ended up mashing up, I think, some GitHub C# code from 6 or 7 years ago with some Indonesian math paper on it, till I finally got there. And to be honest, it is time consuming and it is energy consuming. But it's also rewarding. It's kind of when you're solving Sudoku, when you feel you cracked the whole riddle, you got to this crucial point where it just clicks and everything fills in beautifully. So that's the very rewarding feeling, which me personally helps to overcome all this stress when it comes to research and trying to figure out how something works.
That is really amazing. And looking at your work, it's clear to see that this technical arms race can lead to very clinical work, almost antiseptic. Yeah. And you're looking at algorithms like turning over rocks and looking for worms. To take your work and dirty it up and add all of this really nice organic work to it. And it is inspiring. And it always leads me to the next question, what direction are you leaning towards now in your work? What's inspiring you right now to create amazing work?
To put it very formally and very abstract, what's currently inspiring me are optimization algorithms, which is about the most brutal way of putting it. So optimization is everywhere. So say, for example, you want to build up an image out of torn paper that randomly floats around and just suddenly falls into a shape that it forms an image. That could be done by an optimization algorithm, for example. So, and that's actually what got me started in that direction. And I think I'm finally getting somewhere, but it's just a wide field. And also, when you're getting into those algorithms that sound a bit dry and a bit intimidating, and you research them, after a while, they lose that sense of intimidation. And you see that all those very elaborate papers and very elaborate blogs out there being written about those techniques, they sometimes seem to be written in a way to specifically sound alien or a bit findishly or a bit difficult to understand. And while in reality, it's rather straightforward. But I'm starting to ramble. So back to the question: where do we see this going, or where do I see the style going? apart from these algorithms that I mentioned, I'm also currently interested in real-time engines. So as you might have noticed, we had a few Entagma tutorials about Unreal Engine popping up. And that's what I'm looking into, looking some of the dev builds, some of the more advanced builds, let's put it like that, to see where they are going, rendering-wise, effects-wise. And it's very interesting. I think for some applications, it is very intriguing to use. I don't see it replacing any DCC tool in my pipeline now.
But the real-time aspect must be intriguing. You know, the ability to, once the algorithms are in place or you build your tools, you can then use them on Unreal to play all kinds of fun games.
Exactly, that's the point. I mean, it's perfectly geared. Unreal is perfect if you want to do interaction, if you want to do interactivity. It's super for that. But I was taken by surprise how difficult it is to create inside Unreal.
Yeah, the content creation. Now, this is one thing that I've heard as well from Houdini users that are now starting to get into Unreal. One thing that it seems en masse asking us is to simplify the process. The more you do in Houdini, where it's a controlled environment, so to speak, and then you push it into Unreal and just give me the hooks and the handles seems to be the way forward. You know, we're trying our best. We've got Unreal 2.0 plugin out in the latest production build a couple of weeks ago, and that is just a mammoth release. You know, the ability to run Houdini and inside of Unreal, but it's still not far enough. We're still getting some Houdini users that say, no, I've mastered Houdini. I just want it to perform inside of Unreal.
Let me dive a bit deeper into that Unreal thing. And I think you guys are doing a brilliant job with interfacing Houdini inside of Unreal. And I agree, the tighter it's interfaced with Unreal, the more seamless the workflow between the two of them, the better. I would love to see that, to be able to just use it as one operation system in a way, where Houdini is one part of it, where Unreal is another part of it. I think that's the way to go. That'd be brilliant if we get, or the faster we get at this point, not if, question of when.
Yeah. And of course, we haven't even begun to talk about the advent, or it seems like we're at the dawning of machine learning and AI algorithms. Yeah. And I know side effects, we really have only dabbled a bit just to say, yeah, this is really intriguing. But I think our current tact is just to provide Houdini as a really great tool to create the training sets at this point in time. And so I don't know if those areas are interesting to you as well.
Well, creating training sets is quite close in a way to the stuff, how we approached design projects and commercial projects in trying to build a setup or an algorithm which could iteratively design. So that's very close, absolutely. But what I would like to point out is that you guys are doing a brilliant job with the Python 3 integration you recently released. I really love that. And I can see so much space for playing around and having a playground with AI, with Python libraries, just importing them into Houdini, having fun there. So that gets me very excited. So kudos and thanks for providing that, because I think it's extremely valuable.
Yeah, it was necessary too. In order to do a work in this area, as well as there's a lot of advancements in Python. So yeah, it was a necessity for us. And in hindsight, I don't know, I can't speak for everybody in R&D, but as a casual observer over how R&D works, it looked to be relatively painless in doing this. So
or you have very, very good devs.
Yes, and I'm liable to eat my lunch after this interview is over.
I mean, you know that. I mean, what is your career path, by the way? How did you get started in this industry?
Wow, architecture, believe it or not, and before that, stint in biochemistry, a failed biochemist, then into architecture, and then I early adopter of CAD, and I just decided to sell the Jeep and get an SGI, and Kim Davidson graciously lent me a cut of the software, and I started earning a bit of an income. And I love the software, so I gravitated to it. I literally learned Prisms by just reading the manuals prior to actually getting the software. I read
must have been brutal.
It's just how I'm wired, right? I've got this extraordinarily ADD almost to the point, and I literally learned the software from the manuals. And then so by the time I popped it up, I already knew how to do the point swap. But for me, the big enlightenment, and remember, we're talking about 1993. The point swap itself, I no longer had to write a for each loop, or I no longer had to iterate over my geometry. I just simply could express myself via a simple algorithm with some variables and attributes. And that's what blew me away. And it still blows me away to this day. And, seeing the work that you're doing, it's just so inspiring because, for me right now, it's like, you've done so much. What inspires you? You inspire me. Entagma inspires me. Looking at all the various different ways that you can use these algorithms is what, and also looking at the tutorials that we offer online now and all the great work. And this tool set that is created, it's so modular that and building blockish that it's amazing to see. I think our toughest part was just getting over that barrier of usability for that fat middle ground of artists that were very technical but really had difficulties in dealing with advanced mathematical expressions. And
I think that's a road that you are still on, to be honest.
Oh yeah, for sure. Always getting easier and then making it more complex, right? Yeah. But it's also, I think you're from what you're saying, you also have some really wise words in there, and that is, if you are in this game of motion graphics, you can't stop. You are always looking to learn more about deeper look at materials. I mean, your inspection of doing a wood shader in another render engine was very fun for me to watch, because I'm going, yeah, I know how to do this. Let's see how this other application works, right? It's a way of expressing, solid UV spaces and and let's not call it procedural and parametric, adding parametric constructs on top of it was great. Thank you so much, Mo, for the entertaining discussions, wisdom and advice, and also your incredible background and the direction that you're going to be going to in the near future. So it was an absolute pleasure. Thank you.
Likewise, thanks for having me, although I'm not sure where you saw or heard wisdom in there.